exactly the postulated values of electric field and magnetic field can be utilized to figure out the relationship between the speed of light. Speed of light can be figured out in terms of the mu naught and epsilon naught, mu naught being the permeability of the free space, epsilon naught being the permittivity of free space. Similarly, how exactly the electric amplitude and the magnetic amplitudes are related in terms of the velocity of light. So stay tuned for this particular part and try to understand about it. So students, we got to know about the different forms of Maxwell equations. What are the different Maxwell equations? How exactly they are related to the Faraday's law, the Ampere's law, and how exactly are the waves look like. Further, we also got to know about the equation of the speed of light in terms of the permeability and the permittivity. We also got to know about the relation between the maximum value of the electric field and the magnetic field. So let's now try to use those relations into our some questions. So the first question that comes to us here, what we have, so it says the maximum electric field in a plane electromagnetic wave is 600 newtons per coulomb. So that is the value of electromagnetic field, the maximum value of the electric field, that's equals to 600 newton per coulomb. Now if I further say that the wave is going in the x direction, the electric field is in the y direction, never mind, it doesn't matter. Find the maximum value of the magnetic field and the wave in the wave and its direction. Okay. Now if I have to talk about the maximum value of the magnetic field, the maximum value of magnetic field is going to be equals to E naught divided by C. C we know is 3 into 10 to the power 8. So this becomes 600 divided by 3, and here it is 10 to the power minus 8. So this comes out to be 200 into 10 to the power minus 8, or 2 into 10 to the power minus 6, right? So 2 into 10 to the power minus 6, this can be written as Newton per coulomb, and here meter per second square, right? You can simplify and that's going to give you the answer. Further, we know that the electric field equation is going to be given by something like E naught sine, then we have omega if I take it out. So here I'll get T minus x by c. So this is the equation that I have. So the electric field is going along the x direction. So this is what we have. The magnetic field has to go along the it's oscillating along the y direction. Sorry, the magnetic field has to go along the z direction. So this is going to be given by b naught into sine. This expression remains same, omega into t minus x by c. So this is the equation that we have for electric field and the magnetic field. Now let's move forward. The next question is, the electric field in an electromagnetic wave is given by 50 Newton per coulomb sine omega t minus x by c. Find the energy contained in a cylinder of cross section 10 centimeters square and length 50 along the x-axis. Now how do we do it? The energy, the maximum value of energy that we have is equals to E naught. The electric field, that's equals to E naught, which is equals to 50. And as a result, it says the energy contained in a cylinder. Now the energy per unit volume, if I say, so energy per unit volume, that is the energy density, that is going to be given by half epsilon naught into E naught square, right? As a result, if you try to find out the total amount of energy, so that's going to give you half epsilon naught E naught square into the volume. You know the value of epsilon naught. Epsilon naught has a value which is equals to 8.85 into 10 to the power minus 12. If you are not very sure about it, the other way to get it is that you know that 4 pi epsilon naught has a value which is equals to 9 into 10 to the power 9. So from here, what you can do, epsilon naught can be written as 1 divided by 4 into 22 over 7 into 9 into 10 to the power 9, it is. So effectively you can put this particular expression. So you need to just put this expression here, and volume is given as, so 50 centimeters is going to be, so the volume is going to be equals to 10 into 10 to the power minus 4 into 50 into 10 to the power minus 2, so that becomes 500 into 10 to the power minus 6, or we can say 5 into 10 to the power minus 4 meter cube. So this is the volume that we have. Epsilon naught we have already put in. E naught is 50, so you just need to substitute all of that. Now mind you, here I am not talking about the average energy, it is the total amount of energy that is there, right? So this is the expression which you need to simplify, and that's going to give you the answer. Now let's move forward. As we discussed that when an electromagnetic wave is actually moving, there is some amount of energy that is contained. So when there is an energy that is contained, so we talked about the energy, therefore there is going to be some amount of intensity as well. So what exactly is the intensity? Intensity we know is related to the amplitude square. So let's see how exactly it varies here. So when we are talking about the intensity, here effectively is related to the energy, because amplitude that we are referring to, or amplitude square, is related to the energy content, and therefore the intensity here has to be related to the amount of energy that is contained, or the energy that is crossing per unit area, per unit time, perpendicular to the direction of propagation. So here if I say the direction of propagation is here, so how much is the amount of area crossing per unit area? That is, this is the area, okay? So crossing per unit area per unit time. So how much is the energy that is crossing this area of cross section? So if I say a cylindrical volume with area of cross section A and length c delta t. Why c delta t? Because it's going to cover with a velocity of light, right? And so c into delta t, that's going to be the length of the path covered. Area of cross section into the length of the path covered gives me the volume. So therefore the energy contained in this cylinder crosses the area A time delta t with some speed c. Therefore the total energy contained is going to be how much? Is going to be the average value of energy into the volume. So this is the energy per unit volume, that is the energy density. This gives you the total energy, this is the energy density. So energy density into the volume gives you the total energy, right? And so the intensity as we define is equals to the total energy divided by the area per unit time. So U divided by A delta T, so A into delta T goes off. So what exactly are you going to be left with? You'll be left with, so let's try to simplify this equation. So you get U is given to you as U average into C delta T into A divided by A delta T. Okay, so if I put in this, A goes off, delta T goes off, so you are left with U average into C, right? So this is going to be equals to half epsilon naught E naught square into the velocity C. So this is nothing here. So the answer is intensity is going to be half epsilon naught E naught square into C. So as you see, the intensity here is proportional to the amplitude square. What is the amplitude here? Amplitude is nothing but the electric field intensity or electric field amplitude, right? Okay, let's go further and try to discuss a question. So find the intensity of the wave discussed in the example. So as a result, if you just try to do it, the intensity comes out to be equal to this. So if you just put in all the values, epsilon naught, velocity of light, everything, so that gives me the intensity. Now you remember that if you have energy, so energy is also going to be related as P divided by C. Okay, sorry, P into C. P into C gives you the energy, or the momentum is going to be defined as the amount of energy contained divided by C. So this is energy, not electric field. So energy divided by C, or if you like to put it, so we can also write it as U divided by C. So that gives you more conventional notation, right? So this is the amount of momentum that is carried by it. As a result, so if there is any wave, electric wave or magnetic wave, which is incident on any particular medium, in that case, that wave is going to deliver some amount of energy U, and with that is also going to deliver some momentum P. The momentum P that it delivers is going to be defined as the total energy that is contained in that wave divided by the velocity of light. So if the wave is totally reflected, so you'll have a momentum P, and the reflected momentum is going to be minus P. So as a result, the net momentum delivered is going to be equals to U by C minus U by C. So this comes out to be equals to 2U by C. So this is the amount of momentum that is delivered on that particular surface from where it is getting deflected. So hopefully you understood about whatever we discussed. Now let's get back to doing some problems based on it. Yeah, so that we'll be discussing, some problems we'll be discussing in our next part. Thank you. In this part, what we discussed about the relationship, that is electric field, the amplitude of the electric field E naught is equal to C in times P naught. C is nothing but the velocity of light. In the same way, we got a relationship between the velocity of light in vacuum as equals to 1 over square root of mu naught into epsilon naught. This follows from the Faraday's law and the Ampere's law respectively. Then we also got to know about how the refractive index of any particular medium is actually related to the relative permeability and the relative permittivity. That's a very important concept as far as the relationship with optics is concerned. Now, since we have discussed the complete chapter, now is the next part wherein we'll be trying to understand about some applications of what all we have discussed.